Okay, here is a review of the free body diagrams that you should have constructed from the system schema. So for number one, you want to draw a boundary around the skater. And I should also say, in case you did not read the instructions, you must correct your problems and you will be turning in your corrected worksheet to show that you listened to the video. And you have to have everything correct in order to get full credit. So, boundary around the skater. 2 interactions means I have 2 forces. So on my free body diagram, I have weight is always going straight down. So the weight on the skater by the earth. And then the ice, I have a normal force upward on the skater by the ice. These two are going to be the same length because the skater is not changing motion in the vertical direction. And I don't have any other forces because there's frictionless ice, so nothing going to the left, and there's nothing forcing her to the right. Okay, number 2. A softball player is slowing down as she glides into the base, so you're going to put a boundary around the player. There are 3 interactions, 1, 2, 3, and so there are going to be 3 forces. As always, I have to have my weight going down. The only time I don't have weight going down is when I am not on the earth, when I'm in outer space. I have normal force going up, and it is the same length. So normal force, the weight force on the skater by the earth, normal force on the skater by the ground. She is slowing down. She's moving forward, but she's slowing down. So that means my friction has to be opposite the direction of the slide. So this is force of friction on the, that should be, I've got skater. Should be P. That should be P. That should be P. That should be P by the ground. So make sure you put P on your corrected worksheets. Okay, chandelier. Suspended from the ceiling by a chain. So boundary around the chandelier, I see there are 1, 2 interactions. 2 interactions means there are 2 forces. You have to have a dot. So if you have not put dots in your other ones, do the dot. This is literally what makes it a free body diagram. This dot represents the free body. If you don't have the dot, it's not a free body diagram. So always have weight going down. This is the weight on the chandelier by the earth. And in this case, the tension is pulling up. So it's a tension on the chandelier by the chain. These are the same length because the chandelier is not changing motion up or down. Okay, a bucket of water is being raised from the well at constant speed. Boundary around. 2 interactions, 1, 2. So there are going to be 2 forces. I've got weight going down on the bucket by the earth. It's the same length as the tension going up on the bucket by the rope. Now, suppose that the bucket were accelerating downwards. How would the length of this arrow be different? It would be shorter because if I'm accelerating downwards, I have to have a net force in the downward direction. And so that means the upward arrow has to be shorter than the downward arrow, so the net, when I add them together, it's down. Let me draw that out. So accelerating downwards, this is my weight arrow. My tension arrow has to be shorter so that my net force is down. Okay, skydiver has just left the plane. I've got boundary around the skydiver, have to have the boundary, 1 interaction, have to put on the number of interactions, 1 force. That means on my free body diagram, I only have 1 force. Don't forget the dot. I have weight going down. A little bit later on, I'm going to ask you, does there always have to be an upward force? And I'm going to ask you which question tells you the answer is no. This is an excellent example of I do not have an upward force because there's no upward force. So I do have to have the downward force when I'm on the surface of the earth, which is weight, but I do not have to have an upward force. So important to know. Skydiver descending at constant velocity. Here's my skydiver. This is the way we chose to represent the skydiver. So I've got draw a boundary around the skydiver. 2 interactions, tension, weight, 2 interactions, 2 forces. Make sure you write that down. Dot for the skydiver. Weight going down, weight force on the skydiver by the earth. Tension force, because I'm going at constant velocity, there's no change in motion, so my net force has to be 0. The size of my downward force has to equal the size of my upward force. This is tension on the skydiver by the parachute. Now, suppose that the skydiver was slowing down as he was going down. How would the tension force compare to the weight? So he's slowing down as he's moving down. And in order to do that, my tension force would have to be bigger, because if my velocity is down, in order to slow down, my acceleration has to be up, which means my net force has to be up. So if this is my weight force, that means my tension would have to be longer so that my net force is upwards. Okay, so that would be if I were slowing down while traveling down. Okay, ball is rising in a parabolic trajectory. This is my schema from yesterday. Boundary around the ball. There's one interaction, one force. That is the weight force. So again, this is an excellent example of when I do not have an upward force. All I have is weight going down on the ball by the earth. Number 8 is identical. It doesn't matter where the ball is in the trajectory. It's in free fall, and so the only thing acting on it is the force due to gravity. And so this is what the free body diagram looks like for the force due to gravity. Cork is floating in water. So I draw boundary around the cork, 2 forces, buoyant force, weight force. So I got 2 interactions, 2 forces, dot for the cork, weight on the cork by the earth, and then upwards I have buoyant force on the cork by the water, and these have to be the same length because the cork is floating, it's not rising or sinking. Airplane, straight level flight. I've got boundary around the plane. I've got 1, 2, 3, 4 interactions, which means I have 4 forces on my free body diagram. Dot for the free body. Always have weight going down, so force, weight force on the plane by the earth. I've got lift going up. It's in level flight, so I know the lift has to be the same size as the weight. There's no change in the vertical motion, so force of lift on the plane by the air. And then we also have thrust going forward, force of thrust on the plane by the air. And then drag, we said that it was moving at constant velocity, so I know my drag force has to be the same size as my thrust force. Now, if you made them shorter than lift and weight, that's fine, as long as drag equals thrust and lift equals weight. So force of drag on the plane by the air. Last but not least, nail has been picked up by a magnet, so draw a boundary around the nail. I've got 3 interactions. 3 interactions is 3 forces. So I know that the weight force is going down. So force of weight on the nail by the earth. Now, the normal force is a pushing force, and so it's actually pushing straight down from that corner. If you have it going at an angle, I could probably live with that, but in my universe, that's touching right there, and it's pushing the nail down. I know that seems strange. So I just made it an arbitrary length. I made it less than the weight force, but you really could have made it any length. So this is the normal force on the nail by the magnet. So the upward force, because the nail is just hanging there, this length has to be the combination of this plus this. Now that I look at it, I might have made it a little bit short, but the upward force has to be the sum of the downward forces because there's no change in motion in the vertical direction. So this is force magnetic on the nail by the magnet.